Right, we have a space a DLGNI NPP, and they and TrackIO itself created the dataset, DLGNI NPP and dataset, right?
Yes, yes.
Okay, 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 sir. Thank you, sir.
You will see that linked data set in the project section in the space. Near the project section, it will show which data set is linked. You can click that and go to that data set.
Okay, okay, sir. Thank you, sir.
Okay. So is there any other questions? Like if you have any doubts regarding any particular topics, you can
So
ask
like,
that first. We'll start with
so
that.
like the Hugging Face actually sleeps very much. Like at
High face
the first
actually.
it will sleep. So yeah, the Hugging Face actually sleeps. Like if it is inactive for 2 or 3 days, it will automatically sleep.
Yeah, spaces will go to sleep. That is fine. But the data set
So
will be there. So
okay,
we'll be using
so
the data set. The logs will be present in the data set. So we'll be using that directly.
yeah,
So
so
it,
like when I click on that below link in the project file, there the dataset file is there, and there are many like versions of that. Like what I uploaded in the track IO, so many datasets are coming over there.
yeah, yeah, that is fine. That is fine.
Okay, so I do not need to manually like go and keep checking whether my CN is sleeping or not.
No, no, no. That
Okay,
is not the case.
okay, okay, okay.
Anything else? Okay. Let me start sharing. Okay. So here in VK, we have this memory-based models. So these models came out as the improvement over the plain vanilla RNN. These are also recurrent neural networks, kind of special variants of recurrent neural networks that solves a certain problem that vanilla RNNs doesn't solve. So the vanilla RNNs, the problem was
Sir,
when
what's the
the
quiz two syllabus?
switch to syllabus till week 8,
1 to 8 or week 5 to 8?
1 to 8, 1 to 8. But the weightage of the questions from week 1 to 4 will be lesser compared to that. So you can think like uh, each of the week 5 to 8 will have zero point 0.2 and week 1 to 4 will also combinedly have 0.2 weightage. So that is kind of the distribution of the questions from the next.
And sir, what about the coding questions? Will those also be there from
Coding,
week 1 to 4?
coding the basic like PyTorch snippets description kind of questions will be there, as I said. Like the
So
architecture
usually
will
we
be
only
defined
have
in
week
code.
5 to 8, right, sir? But why this time we have week 1 to 8? Because for most of the
Uh,
other courses we have 5 to 8.
1 to 4, you will have a lesser weightage compared to the other weeks. It's basic only, so I don't think very hard questions will be coming from these weeks. You just have to look into that, like just like a summary. Mostly focus on these later weeks. Okay.
Okay, so one thing I found in that Hugging Face was that when I provided the link of the like the dataset, like the link, so there I found the files and version. Under that, the many things came. So are you talking about that things?
Uh, so those are the files, like so you see an app displayed in the space, right? So those are the files for like
Oh,
booting up the apps.
no, sir, not that, sir. Actually, the dataset link I have provided, when I just copy and paste it in the like the web browser, so it came in the dataset card, data studio files and version, like the thing it came.
Yes, yes, it will have the in a data set. So basically, Hugging Face data set is very similar to a Git repo. It has multiple files. That's it. Okay.
Okay, so yeah,
So
understood. Like okay, okay.
yeah, data set spaces are also like a Git repo in some sense. But when you upload to the Git repo, you can actually deploy Flask-based apps in spaces. So it's also like a Git repo with a deployment feature. That's it. Spaces is a repo with a deployment. Dataset is a repo which is capable of handling large files. So there is something extension of Git called Git large file system, Git LFS. Again, Face uses that to version these files for you. So that is basically Hugging Face. It also, for models also, it uses the same Git LFS to manage the model version. So basically, Hugging Face is very similar to GitHub, but specialized for models, data sets, and application specific code called spaces. That's the difference. You can even use Git to Git push in push data in Hugging Face. You just need to add the proper credentials to uh, thing and do that. So it's basically GitHub for large files. You can think it like that. Okay.
Sir, for the quiz too, we you practice more on the coding questions because sir, this is the first batch of the DL Gen. So we have not PYQ, so that we practice on. So
Coding questions, as I said, it won't be like code writing questions, fill in the blanks questions, kind of that. It will be like
yes.
code understanding question. And the code will be not very technical in nature. It will be structural or descriptional rather than functional. So
Mm.
it's like to describe a maybe an RNN, we will use some code. So a PyTorch code will describe an RNN, and the questions will be based on the architecture of the RNN rather than the uh, what are the parameters this function would need. So those kind of memory-based questions won't be there.
Okay. Okay.
It will be
So
like
we
if,
have asked a question about the RN, anything type of structures, right? And some of the meaningful fill in the blanks, right?
it will be mostly based on the network rather than the code used to create the network.
Okay, sir. Okay.
So basic codes like you might want to look into basic TensorFlow code. What are the simple commands? The array manipulations, the tensor manipulation commands are there, right?
Yes.
Some basic commands. So from week 1 to 4, those you can revise. Other than that, mostly the questions will be like this, not more memory oriented, mostly on understanding oriented.
Yes, sir. So we can proceed to next. Okay.
So like the week seven
Yes,
and 8 are together, like in this PDF.
yes, yes.
Okay.
So this part, so we are going into the memory-based RMS. So the main idea in this one was in the actual vanilla RLM, we face two problems due to the long uh, sequence. When long sequences come, there are two problem arises. One is the vanishing gradient problem and the uh, exploding gradient problems. We saw we can control exploding gradients problems with by clipping the gradients with some maximum limit. But vanishing gradient problem is a very serious problem. You might not be able to detect it because the gradients goes nearly to zero as the length increases. So we saw intermediate solutions, an immediate solution for that, which is the back propagation through time. So sorry, truncated back propagation through time. So we set up a maximum limit, but the disadvantage of that is we cannot hold memory over long intervals. So that context is getting lost. So the models cannot remember things and connections between long sequences. So then there came these memory-based models. Uh, these two memory-based models. One is this LSTM. This is a long short-term memory. So basically, it instead of an improvement over RNM is that it had two hidden states, one for the short-term memory and one for long-term memory. Right? So so let's see this. So this is the uh, yeah. So this is the uh, basic plot diagram that describes how the LSTM looks. It might be looking very complicated when you look at this as first glance, but when you look into it in like idea in comparison with RMN, you can see it is like very similar to RMN. Okay. So what are the hidden states we had in RNN? One is the H, this hidden state, and this input. We had a hidden state and the input, and the output will be based upon the hidden state. Right? The output will be based upon the hidden state. So, but here we have this three gates. So something called as gates. Gates are used in both LSTM and the GRU, which is short for gated recurrent units. So kind of gated recurrent units are some simplifications over long-term memory. We look into that later. So now we focus on this. So there are three gates over here. What target gate, input gate, and output. So if you see the C, the hidden variable or the hidden state C holds the long-term memory, and this one holds the short-term memory, right? Okay. So now uh, this is the hidden state. H holds the short-term memory, and this holds the long-term memory, right? So now we want to use this one. So the previous long-term memory and the current new memory, and we are using a sigmoid function. So this is a sigmoid activation function. There will be weights associated with this. So this each of the gates will have weights associated with this. This multiplication that you see, basically the weights kind of thing. So what is this sigmoid function do? How does the sigmoid function work? It kinds of gives in a value from 0 to 1, right? So based on the this is just not the sigmoid function. This is wx, this h and x. You do a multiplication over here, the weighted sum, and then this is like an activation function. So based upon the current hidden state and the current, you can call this previous hidden state and the current input, you use a weight matrix to like adjust the output of the sigmoid function. So this sigmoid function's output controls how much to forget. So based upon these values, so these parameters that are lying around here within this W, here there is a weight matrix, and this activation controls how much to remember or forget from the old long-term memory, right? So this value will be from whatever is the output of the Wx plus C and the sigmoid will be ranging from 0 to 1. So that says how much that 0 to 1, when you multiply a value with 0 to 1, it's kind of saying how much percentage do remember from the old year, right? So this is remember like forgetting the long-term information. So this is learning these weights associated with this forget gate are learning what to forget. And then we have another gate. So here, this basic thing, here there is this. So this internal state is, we call this C hat as the internal state over here, right? So there is a internal, this state is also called as a cell state, kind of, right? So this will be an internal state. And this internal state is what is the raw output of the previous RNN. Usually the previous RNN, what it will have, a Wx plus H and a tan H function, and that will be your output. So instead of directly, so this output is the direct output from the RNN. So basically this part here is the core thing of the RNN. But here we are not directly outputting this output, but we are internally maintaining this as the current cell state or the this will be the usually the output of the vanilla RNN. After this Wx plus C, you do that. But instead of that, we also have a input gate. So these learns, this also will have a separate weight matrix. The output of this will be between 0 and 1, just like a sigmoid function. So this will control how much of the current input will be taken to update the long-term memory. So this is forget gate, which says how much of the information should I remember to the next state. This says how much of the current information should I remember in the next state. And then this output gates again gates this thing. So this output gates also coming from this one, these two weighted matrix. This says how much should I, so this is kind of the internal cell state is there, right? How much should the next state look into? How much should I give? How much of information should I pass to the next state? So this is how much of the information should I get from the next gate. This is how much information should I give from the current input to the internal cell state. Look over this internal cell state. And with the internal cell state and the information that I get from the previous thing, how much should I pass to the next gate? That is being controlled by the uh, output gate. So you see all this sigmoid, these sigmoids are outputs of a weight matrix. So there is a weight matrix associated with O, there is a weight matrix associated with I, C, and F. Each of this has own weight matrix associated. Right? So that is basically given over there. These are the mathematical equations that is. As I said, there is a weight matrix like weights and biases with activation. So forget gate is basically there is a weights for forgetting and the biases for the forget gate, and you do a dot product with this, right? So taking these two as input, it will multiply with the linear combination of the things to give you how much of the information should I remember. So that's what these weights control, right? And then this is the forget gate. Okay. And then similarly, you have a input gate, which is very same as that. So this candidate or the internal cell state that we saw, right? So this candidate gate is the one that computes the C hat that we saw. So we are calling this WC. So the equations are very similar, weights and biases plus the activation function. So that's why here in this diagram, the weights and biases multiplications are not given, only the activations are given because those are the different things. And the weights and biases thing are like kind of internally assumed it is everywhere. Okay. And this is the input. So this input gate acts as the filter to decide which values from the candidate vector are important. So this will decide which values to take from this one, the candidate. And then there is this output gate, and we combine these things, right? So we also combine the previous cell state and the current cell state to create the new cell state, the candidate. So this will give us a new cell state. So this is the candidate. We call this uh, the candidate. Okay, from the candidate, we kind of predict what is required to be the current cell state, and then we use also the output to say which should be going to the next one. So that is here. So this selects how much of the inputs, like how much of the thing would go out of this one. So how much of the relevant information for the long term input. So it kind of learns when you see a current input, it kind of learns is this kind of necessary, is this an important thing for the next words. For example, you could see about something like this. There may be a word called is or the might come, right? So I kind of not want to remember this in a long-term memory, which kind of not needed. It might be needed for the current state, but it might not be needed for a long-term memory. Maybe I want to just remember the like important words and lose out the. I don't want to remember the non-important words in long term, right? So this kind of controls with the current input, how much of the information should I pass to the next thing? So this kind of controls keeping these kind of words not in the long term memory. So it's kind of that. Sometimes the input gate as we saw, right, it might behave something like this. For example, when a sentence ends, we might don't want to remember certain parts of the sentence anymore. So the input gate kind of learns what kind of information should we can forget. So since assume this is a new sentence that is going as a current input. So based on that, so okay, now I have started the next sentence. So I kind of don't want to remember these certain parts from the previous sentence anymore. So input gate decides that. But the output gate decides, now I have seen this word is kind of not important for the next sentence. So I don't want to remember this. So kind of deals with that. So that's the difference between input and output. Yeah. Okay. So with this output gate, we compute the new hidden state, and these will be passed on to the next step. So I think putting together all equations in a slide, I think this is not safe. So this is the next output. So with the current candidate or the cell state, we are multiplying this. This is a Hardeman product, which is kind of multiplying each values with the output gate values, like a point-wise multiplication kind of thing. Okay.
Sir,
Yes.
so is
Yes.
your screen stuck?
Uh, so how long has been my screen stuck?
So we can see that current state dependency on previous state. That slide we could see.
Okay. Could you see my screen now? The output gate.
Yes, sir. Before that,
Can you see my screen scrolling?
no, sir.
This is the same for everyone.
Yes, the same.
Okay. Yes, now is it okay? Sorry, I'm not presenting. Uh, now, how can you see the screen? Visible? Still no?
The screen is visible, but it gets stuck
Yeah.
once you share.
What do you see in my screen now?
Video, sir, encoder,
See
decoder,
portal,
running.
sir.
Oh, is now the RNN slides visible?
Not yet.
Okay. I think there is a problem with my browser. I'll join in another browser.
And sir, I have a question that why we are using different activation functions at different places, sigmoids and tanh.
Yeah, is my screen visible now?
Yes, sir.
Yeah. Mm. Yeah. So where
Sir,
were
I have a
we?
question
So
on activation function.
yes.
Sir, in the diagram at different places we are using sigmoid and tanh. So what is the
Mm.
logical reason for these?
Okay. So the main logical reason for using sigmoid here is these values acts as gates, which means kind of weightage from 0 to 1 or controlling the power of the signal or the percentage of the signal that is going to the next level, right? But the standard function, so this is like scaled from -1 to 1. So it's basically the tanh function is very similar to the sigmoid, but it is kind of centered around 0. So it can take negative values also, right? So this kind of ensures the propagation of the gradients in both directions, kind of like that. And it kind of performed well in vanilla RMNs. So the idea of tanh function performing in vanilla RMN being used again here. So that is why we use the tanh functions here. So as I said, this part here, this candidate computation is exactly same as computing the output in vanilla RMN, right? Similar to that. So it can alter the uh, output either to negative or positive, like that. These gates, these sigmoid gates that we added, control the scale. So it's kind of scaling factor you can think about. So should I, how much percentage of input should I pass to the next output? So it will be from 0 to 1, right? So if it is 1, I'll pass the whole thing to the next state. If it is 0, I pass nothing. If it is zero point 0.5, I pass half of the information, kind of that. So the intuition is kind of, so the gates will have the sigmoid, and this is the normal RNN part. And here in this celestium, you also have this output. So that is 10H activation. Okay.
Levin, I have some questions before we move
Yes.
on. Actually, for the normal RNN, we were having U and W's, right? U for the hidden and then W for the actual input. Now, from there, now we have created here we have to learn a lot of weights, right?
Yes. So there are lot of weights associated with it.
Because we have now
Yes.
introduced three modules for get input and
One.
output.
So yeah. So there is 1, 2, 3, 4, and 5.
No, here again for H there will be U and X there will be W, right?
Um,
Because it is all shown it as one line, but it is actually
we call this
linear
with some
combination.
suffix. Yeah. WF, like that. We call it for the weights for the forget gate as WF. The weight for the input as WI, and the weights for the candidate WC, and the weight for output as WO, like that. So this these many weights we have. 4 weights totally we have.
That in turn has two, right? One for the hidden, one for the input, not like that.
Yes. So basically, this is kind of combined. So instead of writing WF times H
For
plus
simplicity,
WFX,
the diagram
uh,
was for simplicity, the
so
diagram
it's
has
a
been
two-weight
drawn like
matrix.
this.
So this is same as having a W matrix for H and W matrix for uh, X. So you just
X.
combined it together
Okay.
for
And then the
simplicity. So just
bias.
a notation
Okay.
change. You
Yeah,
can
yeah.
think it of like a notation change.
Yeah, it is basically a linear combination of U
Yes,
into H plus W into X. This is,
yes.
can we go to the drawing, the first one with all the three blocks? So every sigmoid and the tanh will be having a linear combination of XW, X1W, and
Not this one.
HT.
This one will
Yeah,
have
we will
this
go to
multiplication.
that later. We will first
Yeah,
we will go
these
to the
four.
bottom.
These four.
Yeah, these four. So it will be having XT W and HT minus 1U. For all both 3 sigmoid and tan H, this information will be going. Yeah, and then
Yes.
the f of t is the whatever function, sigmoid function of this linear combination will come. So forget function is very clear. How much to forget? Because you have a 0 to 1 will be there. So multiplication of 0 to 1, it will be less always from the output of the forget function after the multiplication. But coming to the input gate, the sigmoid will be giving us how much to add, but the tan h will be varying. It is whether it is negative or positive. Is it like that?
Yeah, this is basically the RNN unit. This is basically the RNN unit. If you see that. So this two weights and a tan H function gives you the hidden state. So this is the hidden state in the actual vanilla RNN kind of. This part can be thought of like that. This part, this part. Without the
Because
gate, without this
finally that
input
output
gate,
actually goes to the long term, right? The input gate, basically it is going to again to the long term, right? Because from the long term it comes
yes,
and added.
yes,
There is
yes.
an add
But
function.
also this what do you say? So this input gate, these two are added to get like going to the next cell state, right? But so there were different architectures are there, right? So sometimes each there will be multiple outputs generated. Output in the sense that for each x there will be some y generated. So the y will be generated from this summation kind of thing. So y will be also generated. So that is not given in this diagram.
Yeah,
So in an
basically
RNN,
I forget and then add for this. That is very clear because I first
uh,
forget based on my input what I need to forget I'm doing from the long term, and then based on my
yes,
input what I need to add to the
yeah.
long term is the next block. Correct?
Uh, Not only what I add to the long term, so what I add to the long term uh, from the current hidden state or the current candidate.
Yeah,
So this
current
is the
candidate.
vanilla RNN equation. How much of the current information could I add?
Hmm. Hmm. But we multiply this before, right?
This,
IT into IT into the
so this is basically the vanilla RNN part. So the vanilla RNN part will have this,
okay.
right? So from this output, we are this. So this controls how much of this value will go to
Yes.
the next one.
Yeah. Yeah, because it is plus to minus. So how much? And then this will give the IT will be giving the weightage because it is 0 to 1.
Yes,
IT will be 0 to 1 because it is sigmoid. And then this epsilon t is minus 1 to 1. So it can either add or it can detect.
yes.
Correct? And then this is for the long term. Again, when we go in the input, it is just adjusting the long term based on the current, the second block.
Yes. So this is the cell state. So the new cell state will be updated based upon this forget and the input, right?
Mhm.
And the next cell state will be computed using the output gate. So for the next hidden state, this next hidden state, we will use the output of this CT, this cell state, the current cell state as we call it, and we multiply it with the output like that. So this will be the hidden state, right? And the CT will be the cell state, the next cell state that is going on. So there will be H and CT. Sometimes there will be also output. So that is actually not given in this diagram. Sometimes we'll have the output also.
Can we go
So
to the
just like
drawing?
in the,
Can we go to the block diagram? Yeah.
yeah,
Here.
just first let me go to this. Yeah, here if you see, there will be weights associated. This is the two weight matrices which will produce the hidden state. And there will be also a weight matrix that is producing the Y, right? For each time step, it will produce the Y. So that weight matrix is also there. Uh, I think here it is called. This HY is there, right? This matrix. So all the input, all the gates at the bottom layer had these two weights, WHH and XH. That is combined as WF, WI, WC, and all. So this kind of this weight, which produces the output, is not kind of mentioned in this block diagram.
Yeah, the
That
block
will be
diagram
carried out from the.
misses the Y, misses the Y. Yes.
So it is talking about the internal two cell state, how these two states propagate to the next one. That is
Yeah.
what this diagram is talking about.
Where is that HT in the top is going? Where from the output gate, one HT goes to the next. There is one more HT going to the top. What is that doing? Why we split that
I
HT?
think both are the same thing. I think this might be there to denote this hidden state is used to compute the output. There might be another weight over here.
Okay,
And
okay. That is okay. Yeah, we can understand that. Yes, yes, yes. And then the other HT is going like HT minus
to the
one, it
next
goes to
step.
the next one.
Yes,
Oh, okay. And the CT, yes, CT minus one, CT is going. And then this HT is for the output. So, okay. That is very clear.
yes. So you see, the C3 is kind of multiplied with this output gate to give the next HT. So here it is multiplication, this one and this one combining to produce the H.
Okay, clear. Clear. For the long term, I forget first for my based on my current input,
So
and
as you
short
see,
term
you can
and
kind of see this. So this is like this gate kind of controls how much of the long-term memory should I pass to the next short-term memory.
yes, 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 that is also happening.
So it's
Yeah.
kind of now I need to remember the something from past. So it's kind of deciding that.
Yeah. Okay. Now doing this, how my problem of diminishing gradient is getting is avoided. Doing this, how
Uh,
my gradient diminish problem we are resolving it. How it is getting
okay,
resolved.
how it is getting resolved. Yeah. So the main understanding
Because that is
is
the objective, right?
sorry.
Because we started with
Yeah,
that
yeah.
problem and then trying to say the solution, coming to the solution.
Yes, yes. Uh, this part. So, what is the usual thing that we do to forward the next stage? It's like multiplying the input and uh, okay. So I think let me put this way. Okay. So we did some WX plus WXH. Can combine them plus B. This every time WXH. Sorry. And then apply the W matrix over this one, uh, kind of like this. This is what happens, right? So essentially, this one is multiplied with more W's, right? But here, if you see, let's talk about the hidden state. So this hidden state is not just WX plus V. So this is coming from the long-term memory also, and also it's kind of coming from the long-term memory. So this is adding to the long-term memory, right? So this is adding to the long-term memory, and this output is coming from the short-term memory. Sorry, this. Okay. So now when we do this sigmoid activation function, we are actually multiplying this one with some value. So it is like, mm, for this one, well, when the gradients goes backward to this one, uh, we are kind of scaling the gradients also. So since this, and there is this additive nature, right? So for example, uh, this long-term memory kind of keeps track of the, so this kind of like skip connection. So this long-term memory kind of acts like skip connections, uh, providing this data necessarily to the next one. So this current input, when you propagate backward, not whole of this might be passed to the backward, and there is this additive nature around there, right? So sometimes it will pass here and this pass here. So let me see if I can put this out clearly. Mm, I think we will discuss this GRU first, and then I think it will be simpler
Yeah, yeah, sure, sure,
that
sure,
way.
sure.
Yeah. Okay. So let's see about this GRU first, and let's come back to this problem of how this two are solving. Let me see if I could put that in clear terms. Okay. So now let's go with the GRU. So here, this is a like kind of alternatively introduces an alternative to this LSTM. So here, instead of three gates, there are two gates, and there is no separate cell state. So which means we are not having a long-term and short-term memory separately anymore. There is a hidden state, but that is controlled to two gates. One is an update gate and a reset gate. So the idea is kind of very simple. You see the update gate kind of controls how much of the input, or this reset gate controls how much of the input is uh, multiplied with the uh, hidden state. So controls how much of the past information to forget, kind of that. So it's like that. So this one update gate, should I pass this information to the next state? So it kind of decides that. So this is like a forget gate, and this is like a input and the update gate combined together. Sorry, input and
No, the
output
reset
gate
gate is
combined
not
together.
clear, right? See, the multiplication is only happening for the current input, but HT minus 1, what happens? This multiplication of this current input xt into the sigmoid function of this, it goes and then HT minus 1 directly comes. There is nothing happens there. Either there should be a summing function, or there should be, okay, reset means
I I think
something
I
should
think I think
happen.
there is a yeah. So you can see here. Um, let's see this. Actually, WHT minus 1 is used in the reset key, right? There is something. mm,
Because the
Let
HT
me see.
minus 1 should be
Yeah,
reset with this
yeah.
whatever
Actually,
HT.
actually, actually, because I think there should be a connection over here also. This
Uh-huh.
HT minus 1 is
Uh-huh.
actually used in the reset kit, which means um, you see this, the sigmoid output, the
Sigmoid is
input is the H is also an input, right?
yeah, yeah, yeah,
To
yeah,
this
yeah.
one. So that connection, so this for the sigmoid, the H minus
It
key
should
should be
come
also
here. Okay,
coming here.
okay. Then it is okay. Then it maybe this has to come here. Maybe the output goes there. Okay, this is
Yeah.
clear.
And
The
then,
formula.
yeah,
Maybe
yes.
the entire
Uh,
multiplication symbol has to go at the very top in the drawing. It should be pushed to
uh,
the top. That line,
Not
no,
like
it's
that also. Uh, no, that is fine, but also it should come as the input to this gate, right?
yeah. Both should happen. Yeah.
Yeah, yeah. So that is the reset state. So then that input is controlled by this update gate. Let's see this equation. So this is the update gates. How much of the previous hidden state is carried to the next one. So it controls how much previous hidden state is carried to the next one. Um, okay, so that is okay. Let's see. Mm, okay. Let me connect these equations with the diagram. So this gate has this reset state RT. So we like this, right? Mm, yeah. So here there should be one thing over here. So this will get how much of the previous hidden state. So this value, how much of this value should pass through will be maintained by, will be learned by the parameters over here. So these two parameters of H1, this one, these two weights learns how much of this hidden state to pass to the next one. So that is being told here. So that will be like that. So this will be the new hidden state. So here, if you see, here will be the new hidden state that H is, sorry. So the filtered previous hidden state will be here. And with this filtered previous hidden state, we will be computing this one. So this gate controls. So the input to the gates are both X and T. So these two gates have both the X and T as the input. So this H and X are both inputs to these gates, two gates. Okay. And then finally, uh, we combine this one. So this is the R, which is the gate value that we got from the reset gate. We like multiply this. So this is the point-wise multiplication or the Hardeman product. So this will produce some range of values between 0 to 1, with which we multiply the previous hidden state. So this will be used as the like this gate controls how much to put this. And then this is the candidate. So here the candidate is computed here. This is the candidate. So this candidate, uh, the value of the reset gate and the very down with this diagram. So this is fine. And
Sir, is
then
there
there is a
a site
weakness.
where you can show us visually?
Sorry,
Is there any site where you can show us through visual?
let me check. In supplementary resources, there might be one. Uh, something like that. It won't have any based element. Yeah, I think it is there. Yes. Mm, CRE, still is there. I think this is about CRE, the diagram is not there. This is update and reset gate equations. So the equations, let's compare this one. Okay, so this is our candidate hidden state, like the vanilla RNN part over here, right? So this tan H, after this tan H, whatever value comes is the vanilla hidden state, that part. We are multiplying that with some uh, value that is coming out of this set, which is the update gate. And also we are combining uh, this one. So these two gates are fine. And this is the candidate. So candidate is like the vanilla RNN part, but also instead of directly passing the hidden state of the previous one, so this is the vanilla RNN part over here. So this is the vanilla RNN part. This part. This part is the vanilla RNN part. But we are also instead of directly giving it this one, instead of directly giving the WH minus T, we are passing the input of that. Um, so to compute this output, actually this gated HT is used. In the diagram is not showing that connection also. So this gated, whatever is coming from the reset is actually used to compute that one. And then this update gate is also, so the previous H minus T is also multiplied with this one. And then, so this is like, so you see this equation. So this equation is like combined equation. So you see this is set and this is set minus 1. 1 minus set. So the idea of this equation is that the new, so as I said, the output and uh, input gates kind of combined in this as an update gate, right? So this determines the mixing ratio kind of that. How much to take from the previous and the how much to give to the next one, how much to pick from this current candidate is kind of determined by the single variable like this. So if you take more from here, so the net quantity is kind of in the ratio of 1. So that is the main idea here. So let me see if I can sync this completely to the diagram. Okay, so how it should look like is, so this HT minus 1 is used with this one. So there is a weight matrix combining these two inputs to create this reset signal, which is multiplied with the previous HT. And now this previous HT is kind of given to the input to the stand H function instead of the original HT. So that is what happens in the vanilla RNN. But here, whatever is coming out of the reset gate is given to the thing, this vanilla RNN part to create the candidate. And this thing that you see here is what it is saying is this is set. Set is taking how much you should take from the current candidate and set minus one or one minus set. So that is what this diagram is representing. So one minus set is taken from the previous hidden state or the previous thing that we filtered, this previous hidden state. Sorry, this H. So 1 minus should come here, right then. Okay. So 1 minus should actually come here. This is the candidate, right? There is something very much wrong with this diagram. Mm. 1 minus set is used for this candidate, and the set is used for the previous thing. Not sure if I could.
Levin, the previous
Yes.
one, the story was very clear, right? We just from the history we first remove, and then we add, and then we take it to the next stage. That story was at least here. It is a bit
Yeah, yeah,
confusing. ZRU is
yeah, yeah.
not.
So let me like simplify it, try to
You can
simplify it one
explain
more
the
time.
actual leaving this. You can leave this drawing, and then you can explain what is GRU in general, so that from there we can
Yeah,
go
yeah.
through this
Yeah,
slides
yeah.
and then.
So I am just using this diagram for the reference, so don't see it very carefully. So I'll just go through it. So this is the vanilla RNN part that we have in the RNN, right? The tan H with some weight matter. So here, to compute this candidate, we don't want to use the hidden state directly. So usually we use this X and the hidden state to compute this candidate. Instead of that, we will be using the gated value from this one. So to compute this, actually we use a gate that called reset gate to gate this previous hidden state and then use that gated hidden state to compute the current candidate. So this reset gate is controlling how much of the previous thing is added to compute the current candidate. So this is like a forget kind of gate that acts as kind of like a forget gate. How much of information from previous thing to take into compute the current candidate. So that is what this reset uh, says. So with these two values, we are computing. This is the gate. So this gate is computing how much of information should I pass to compute the next hidden state. Sorry, next candidate. If you see this R is used in this candidate equation. This candidate equation is the normal kind of vanilla Arman equation. The only change is that we are getting the previous state. So this is the vanilla Arman equation with a gated reset. This is the additional thing that is coming up in the normal vanilla RNN equation, right? Do you see this? Without this multiplication of this RT, the remaining is the vanilla RN. Is that clear? So now what does the reset gate do? It controls how much of the previous state is considered to compute the current candidate. So in both LSTM and GRU, the candidate is the kind of vanilla RNN part. How when it is computed same as the how vanilla RNN is computed. Okay. If this is clear, this R is just another gate which uses the previous hidden state and the current input to get a value between 0 to 1. Okay. Is this part clear? So to compute the candidate, we use the vanilla RNN equation. But together with that, we add a gate to the previous hidden state. And this gate value is again a weighted combination or some linear combination of the previous ht and the xt to a sigmoid function. That gives you some scale between 0 to 1. Right? Am I there?
So this reset is again we just
It
try
kind of
to
acts like a forget gate.
same
Kind
like
of acts.
forget only. It's kind of a forget
Yes.
only.
Yes.
But here the difference between the previous one and this one is here there we
The
forget
previous
and then
one, there were
add
so
forget and then
there
we
we
add. Here
also
we
had
don't.
one more state. There we had a long-term state also. The C also we have. But here we are directly doing it in the H itself.
H itself. Okay. Okay. We don't have a short term, long term. We just have only H, wherein we just reset. Only this
Yes.
is the difference.
I reset kind of controls what to forget. You can
Hmm.
what to forget and it kind of controls that.
Okay. Yeah, reset is
Uh,
always history removal only. Like
yes.
in our life, right? We go for a reset. You take a break, like this.
Yeah.
You're too much overdone in your work or in your with your life. You just want to take a reset. Something like that. We can take it.
Yeah. So now you have this reset. Then understanding this set is kind of very simple. You see the final output or the next hidden state is computed by mixing the current previous hidden state and the current candidate value. So it's kind of you can think it like the uh, mixing that is happening. The set T is controlling how much to take from what. This is a 0 to 1 value. So this is point 0.2. I take point 0.2 of this and point 0.8 of this. So it's like a mixing ratio kind of thing. And this is also computed using just like any other gate. You see this one, same equation, same equation. Just we have different weights. These two are exactly same equation with the R replaced with Z, right? So all the gate equation looks very same. The gate equations are sigmoid with linear combinations of inputs and the hidden states. Okay, this gate equations all are
Clear,
same.
clear, Levan.
Yeah. And then this gate is basically this one controls how much to remember from the previous hidden state. This one controls how much to mix both the current hidden state and the previous hidden state. This is kind of a mixing ratio. Is that clear?
Clear, clear.
Okay. Okay. I think we now may want to see this part of why this is solving this problems, right? Um, let me see.
Maybe the lecture professor should have addressed, right? In the because he was always telling in week 7, this is week 8, right? Week 7 lecture, he was telling this problem of diminishing gradient is there, and this LSTM and this GNU are all advanced thing which takes care. But how, maybe in the slides it should be there, right? How it is taking care.
Hmm. Actually, there was a resource in which this is actually discussed. Hmm, let me check.
In the LSTM, at least you have that add and subtract block. You remove the long term, you remove and then add something for the existing, so that you don't actually make it so low.
Uh, in that sense,
That-
you kind of have that in uh,
because here
here
everything
also,
is
right?
multiplication block, the GNU. At least LSTM you have an add block, so that
So
it
this part is exactly same as what we have in the gated GRU, computing the next hidden state. Instead of forget, we have these two things are kind of handled by the update. We see that. So that is fine. Um, okay. Okay. Yes. So let's see how the Hutch is propagating backward, right? So the Hutch is the output of it is kind of combined from uh, this output gate and the candidate that is coming over there after the input gate. These two are added. Yes, the idea is like that, right? So here, not only just the hidden state is going to the next one, but also this candidate, some information from the candidate is also getting passed to the hidden state, right? So when you back propagate, the previous hidden state will also have some information from the long-term information will be there. So that will also add to the computation of this one, keeping the gradients in place. So that is the idea, right? So the last equation, if you see the, what is this final equation? Yes. So in this final equation, you have a multiplication with this tan h of c, right? So this what will be the output from this one? 1 2 minus 1, right?
Yeah.
So that kind of uh, keeps the gradients. So what is the derivative of tan h function? So the derivative of
1 minus secant square.
yes, something like
Minus
that,
10
right?
squares.
1 minus tan h square.
Tan h square.
Uh, yeah, in the sense, if this tan h square is always positive, uh, let's see. So when we pass this backwards, mm, I think without the proper derivation, it might not make sense, I guess. So actually, there was a proper derivation in somewhere. Let me see if I could find that. Give me a minute. I think I'm not able to find that derivation. Maybe I'll bring it up in the next session, I guess. The next session, I'll like take out that derivation of comparing this both gradient back propagation equations with LSTM and the RNN. So with that derivation, you will be able to understand. So I think in the next session, I'll bring that derivation. It's kind of not easily find it like this. Okay.
Thanks, Lim.
Okay. Yeah. Yeah. So now I think we can move forward with this one. Yeah. Okay. Yeah. So uh, this idea of bidirectional RNN. So the previous RNN structures. So we modeled everything as the uh, like the next output or the current output will be dependent on the previous inputs. Sometimes some the current output might depend upon the next inputs also, whatever is coming next. Like uh, sometimes the objects are depending upon the sentence structure. So mostly bidirectional RNNs are used in this kind of sentence prediction where you have the full sentence at the same time. You cannot use bidirectional RNN in a time series based thing because in a time series prediction thing, usually the current or the feature will be depend upon only the past. You don't have the feature to predict the future. But in a sentence kind of things, you have this whole sentence available. When so this in the current this kind of actually this bidirectional use RNNs are used mostly in this machine translation task. So machine translation is a sense where the English sentence is converted into a French sentence, right? So in that case, sometimes for the current word, the word orderings might differ in languages. So English might have subject, verb, object ordering, and but some other language might have a subject, object, verb ordering. So then to produce the current white output, you kind of actually want to know the forward what is there in next to predict the current output, right? So that is the intuition of kind of using bidirectional RNN. It might not be useful in other scenarios, but sentence translation, sentence uh, this kind of translations, it is kind of most commonly used bidirectional RNN. So that's the intuition. So here the same thing. There will be a forward RNN layer and a backward RNN layer. The inputs goes to and the outputs are predicted by combining both the hidden states of the forward pass and the backward pass. It is like that. So you have a in the forward hidden state and a backward hidden state, and outputs combine both hidden state to predict out. So this output to predict this output, you have you kind of know what is there after and what is there before also. That is the one change of thing in the bidirectional. It is mostly used in machine translation things. Yeah. Sometimes for uh, this is called the masked language modeling task. When people language model, this is kind of used as an unsupervised task to learn language models. So you take a sentence, you blank out certain words, ask the model to fill it. So it is still nowadays used as a very popular uh, self unsupervised pre-training method for text data. Most of the models, like even the transformer models, use this task to learn the structure of the language. Right? So, so this is the how RNN works. So it's reading from there. It's happy. So both of this thing is combined to predict the new one. Yeah. And then there comes this encoder-decoder architecture. So the encoder-decoder architecture in the sense that, so there is this sequence-to-sequence challenge. So as I said, this let's consider the machine translation as a task now. So now I am kind of translating an English sentence to a French sentence, but sometimes the number of words that are used to say the sentence in English and French might differ, right? So there might not be a word to word mapping for the translation thing. Then how do we handle that? That's where it comes this encoder decoder architecture, where you you run an RNN, you run an RNN to produce a single output, which is called a context vector, which contains the internal meaning of the sentence. So this vector kind of encodes the meaning of the whole sentence into a single vector. And then another RNN kind of, so this will have, so these are different ways of using RNNs, right? So what are we discussing about is different ways of using RNN. So there are kind of four different ways of using RNN. So one way is like sequence to sequence. Sequence to sequences, you get a input and you predict one output at the same time. So that's what we saw in the previous thing, right? So with single RNN also, you can have sequence to sequence. Every hidden state can have one output. Sometimes we can have only a single output. For example, classifying sentence classification. If you are talking about sentence classification task, you can have an RNN and you'll have a final output only after going to all the hidden state. You can have a single output which says what class is that, right? So that is one way to use RNN. Sequence to sequences, for every hidden state you predict the output. That is sequence to sequence modeling. This modeling is the encoder decoder modeling. So the idea is that you put inputs and pass it through hidden states and finally produce a vector that kind of encodes all the information in that sentence or a meaning of that sentence into a vector. And now this meaning is getting translated to a different language or a different sequence using this decoder RNN. So this takes this context vector as the initial hidden state value and runs the same thing to generate multiple sequences. So now this length of this sentence and length of this sentence can differ because the whole sentence is kind of encoded into a context vector. I mean, the meaning of the whole sentence is encoded into that context vector. That is the idea of encoder decoder architecture. Okay, so these are like some basic things. How do you set up everything? And masking, what is, yeah, this BILU are like, these are some scores to metrics that are used in this to evaluate the language understanding quality of that. Mm, okay. So this is like, so this section, what it is deals about is, so in any model, you have these two things. One is the loss function and the evaluation metric. How do you evaluate these things? In a classification task, what will be the evaluation metric? It will be either F1 score, accuracy, those things. In a regression task, you will have MSE, R2 score, things like that. So now in a sequence to sequence prediction task, what can be the loss functions or the metrics. So in a sequence to sequence task, there is just not one output that you have to predict, right? You have many outputs that you predict. So how do you uh, how do you define a metric so that we kind of get how much of the sequence is predicted correctly? So we want to be able to tell that, right? So this blue score is kind of uh, trying to predict that. So this is mostly in this blue score is used in this sequence to sequence modeling, right? So you have so this is evaluated by predicting how much of the n-grams are matched correctly. So that is the idea. So from 1 to k, let's see. So continuous n-gram sequence. Mm, Okay, let me. Yeah, so this k is kind of the parameter in this blue score. Okay, so we can set blue score with some certain k, uh, with which kind of use. It is like setting top k precision. So have you heard about top k precision metrics? So this is like so in usual precision metric, we only see what is the predicted output and the actual output to say that, right? So there is something called as precision at 3, which means if the correct output is present in the top 3 prediction, then it is correct. It is considered correct. So this is something like that. That is the parameter of the evaluation metric. So you can actually parameterize certain evaluation metrics like that. So here this K is the parameter of the blue score. So what is the highest longest sequence that I want to predict correctly? So that is at that parameter you can set. And this talks about the precision of the n-grams. So what is the precision that the correct words are matching in the sequence? So we are weighing that by the 1 by k, the whole thing by 1 by k. And then here the length of the variable. So this now 0 now okay. So this part let's see this 1 minus len of spread minus len of label. So the actual length of the label and the predicted length. So if the actual length of the label is higher, so then this value would be more than 1, which means this will go to 0. In function that will go to 0, the exponential of 0 will go to 1. So if the length of predicted value is less, this will be uh, higher. Right? If the length of predicted value is less, this will go to 0. Uh, x of 0 will be 1. And if this is higher, then it will be the predicted length is higher. This will shrink. So this whole term will shrink, and that will be a positive, small positive value will be there, which will be used. So x power a value less than 1 will be a very low value. So it kind of scales that. So if the prediction is longer, it kind of scales this weighting term over there. The prediction is smaller, it will be 1. The whole thing will be considered kind of like that. Okay. So this is the precision of n-grams. What does the precision of n-grams means? how many n-grams are correct. For example, 1 gram means how many word-to-word matching are correct. 2 grams means how many uh, two-word combinations are present in both target and the predicted sequence that are matching, like that. So the precision means how much actual by total by two positives, right? So it's like that. Out of the total words, a total 2 grams, take every 2 grams and then predict how much is there in the actual sequence. It's like precision by this trading in grams. So you can set the value of k and you can take as much as that. And then you wait by this length component to find in the blue score. It kind of combines different precisions. So the precision of how much the language model is kind of predicting correct, right? So that is kind of the idea behind this blue score. So this is kind of a numerical example. So unigram precision is like, so there is A, B, C, D, E, F, and the predicted sequence is A, B. Unigram is A is correct, B is correct, so 2 match, so 1, full precision. Bigram prediction is also there because this one token is there in this one. So that is also 1. Okay. This one is the brevity penalty. As I said, this component, the length component is there. This is called as the brevity penalty, which means if the predicted sequence is shorter than the uh, thing, it will reduce the score. The kind of that, right? So that is the brevity penalty. It is not fully predicting the sequence. So that is the idea, right? So I think there might be another example, or that is the only example, I guess. That is the only example. So assume if instead of B here, there was C was there. In the unigram thing, you will actually match the this A is present and the B is present. But bigram, A AC is not present, so the precision will be lower there. So that kind of things will happen. So predicting the sequence, so unigram, so we are considering K with 2. So this is the parameter that you can set for the metric. So to compute the blue metric, you can parameterize that with the maximum K that you want to check. And then this term is the brevity penalty. So if the target length, this predicted length is less, it will be penalizing the overall score. So because as you can see here, without brevity penalty, you can actually have a full score with this unigram and bigram precision, but it is not just that it doesn't fully predict the full sequence. Yeah, so as I said here, where this encoder decoder can be used is that when this sentence length is different, you cannot use the sequence to sequence this uh, non-encoder decoder models. You can use sequence encoder models. Summarization also this is used. When this output and input length varies, this encoder decoder architecture are used, where you can encode the information from a 500 word article into a context vector and generate a 500 word summary of it. Question answering is also there. So encoder decoders are also used in this kind of task. So nowadays, these individual architectures are not very widely used. As you can see, as you know, there are like uh, certain models called as LLMs that can actually do all of these in a very unified manner. So they also have some limitations, and they were like it's not they are the final thing that we can give. There are also improvements happening over those things. Yeah. So then there is one more thing uh, about sequence prediction, right? So the way we are predicting, how we are predicting? So we are finding one word. So the output y, as I said, when we are predicting next word, will be a softmax layer, right? So for each input, you will have some y value, which will be a probability distribution over certain words. What I said initially was we usually take the word with the highest probability at each time step. But that is what we call as a greedy search approach because sometimes I predict this current word, right? And next word, uh, it might not be always the current highest word produces a sentence with the overall highest probability. So the probability distribution over one word is the thing that we get out of the output. We don't get the probability distribution over the whole sentence, right? So that's where certain methods called beam search came up. So basically, the exhaustive search is like you take out all the probabilities of all the words in all time steps and then compute the uh, overall probability of all possible different sentences, finding the optimal sentence which has the highest probability. That is one way. Then this in between these two things, there comes a compromise called beam search. What is beam search? You limit the time step, just that. So let me, I think there would be an example how it goes. You choose a beam size, right? And now when we starting our input, first tokens will be given, right? First set of tokens will be there. You take the top k tokens. You don't take all the values, all the softmax. You take the top k possible words, and then you predict the next set of words, right? The next set of words, you predict this. So Uh, as I said, the previous y value sometimes might be given to the input to predict the next word in the auto-regressive setup, right? In an auto-regressive setup, the previous y value will be also given to the input to predict the next one. In that way, uh, only giving the first value of the top value to the thing might not be a good idea to produce the output. So we give this k different values to predict the next set of outputs. So that's how I said we are going to predict the sentence with the higher probability rather than this one. So instead of just using the top value to we use this auto-regressive input, we use the top k value to predict k different outputs again. That's what here. So these are for k equal to 2. So the softmax layer predicts these two things, and we use this as input to predict. So in here, it's not always top two at each thing. We'll be taking overall top two. So from the search beams, so this is what we are calling beams. We always have two things. So if the size is two, we'll be using two only. So for this input, what is highest value? We take. For this input, what is highest value? It's not like for this input, what is highest value? It's like sometimes this A and C might have a higher probability than C and any of this. In that case, we take AC only. So we keep two high probable outcomes when k is equal to 2. It's kind of like that. It's not like one should go to this branch and one should go to that branch. It's like now we have 5 values, out of which these are the top 2k. And now we have these 10 values and we should select the top 2k. Sorry, top k, which is sometimes the probability of A and B, and A and C will be the next second probable combination rather than C and any of these. Right? Then we choose A, B, and AC, and we'll continue the beams from there. So that's how beam search works. Right? So greedy search is kind of a special case of beam search when we set beam size to 1. When we take only the top thing from that. Any doubts? Okay, everyone. I think if there are no doubts, so we can post the session. Now, the next week, I'll bring in that derivation for how LSTM is controlling the vanishing gradient problem. Also, we'll look into the week 9 next week. Okay. Thank you.
Thank you.